Okay, so we have seen that when the energy levels are different, then the particle distribution also will be different. So, when we talked about non-interacting particles in two different boxes, we saw that the particles were equally distributed. Then when we calculated for different types of particles in different energy levels, and thereafter we calculated the probability distributions of particle being at a particular level, what we found is that as the energy increases, the number of particle decreases in an exponential manner for the classical particles which are distinguishable, and that is what is known as Maxwell-Boltzmann distribution. And then we went on and showed that for bosons which are indistinguishable particles, but can occupy several particles can occupy in one level, has a different type of distribution called Bose-Einstein distribution. And then we showed that for fermions which have half integral spins and they are indistinguishable, but only two of them can be in the same level, maximum two of them can be in the same level. In that case, there was a different Fermi-Dirac distributions that took place. Now, I will show you one demonstrations of our own simulations done by my PhD students Raymond with the help of Abhijit to make the movie, is that we show that when we use different energies in different boxes, then no longer we are going to get the same distribution of the particles. So, here there are three boxes, one box is having 0 energy, another is -2, another is -5, and you see initially the particles all start from middle and they get distributed in other two boxes. Now, we will wait for some time for the simulations to continue. These simulations typically use Lennard-Jones type of particles without any interactions, but in this particular case we have used interactions in two of the boxes. They are given by here. This units are in kilojoule per mole that we are going to show. What you are observing here is that no longer the distribution of particles in three different boxes is same. The distribution is no longer same, and rather we see that there are more particles on the right box than in the middle box than in the left box when the system reaches equilibrium. And you know that system reaches equilibrium when the entropy becomes maximum. So, therefore, an entropy will be maximum when the particle distributions will follow Maxwell-Boltzmann distribution, which means in this case an exponential distribution. So, as you mentioned that three different boxes have three different values of energy, that means the particles face different energy values, and the temperature is kept at 300 Kelvin, which is very important. And at 300 Kelvin the kBT value, Kb is Boltzmann constant, kBT for 1 mole comes to be around 2.5 kilojoule. And when you calculate now using Boltzmann distribution the number of particles in the right box divided by number of particles in the left box, then you get this, because let us say your Ni is proportional to the power minus Ei by kBT. In that case, then N1 by N2 will become e to the power minus E1 minus E2 by kBT, and that is what we are showing here. And we put the values and we get around 3.3 times of the right box will have 3.3 times of the middle box, and then we compare middle box with the left box, again use the same energy the energy values that are there mentioned, -2 is for the middle box and 0 for the left box, and what we get is 2.2. Now, let us compare with the equilibrium values of the simulations which are right now there approximately. So, at equilibrium, which is calculated by averaging over 3 nanosecond simulations at the end of equilibration period of the simulation. We are not going to go into detail of that, but we have taken care. So, the average number is coming out to be 138 for the right box and 43 for the middle box and 19 for the left box. And when we take the ratios of the number, we get 3.2 for the ratios of right box and middle box, and we get 2.3 for the ratios of the middle box and the left box. So, this is just from the simulations, and this is what we expect from the Boltzmann distributions based on the energy of individual boxes. And you see remarkably these values 3.3 and 3.2 are very close, and 2.2 and 2.3 are also very close. 2.2 and 2.3 are very close, and 3.2 and 3.3 are very close. So, what we see here, what I demonstrate here is that when there will be different energies, then the particle will occupy according to Boltzmann distributions if it has the distinguishable properties, which and the classical particles we know that that has a distinguishable properties, and therefore, it is following that particular distribution. Another important thing about the Boltzmann distribution is that the energy is scaled by kBT, which means that if the temperature increases, then this factor. So, if temperature increases, then 1 by kBT becomes smaller, and therefore, this factor becomes smaller. So, even if the energy difference is higher, if the temperature becomes higher, then the exponential factor reduces, and that will essentially, which means that this ratio that we observe will actually reduce, which means that particle will start occupying higher and higher energy levels. So, exactly the same simulation is done at a higher temperature 700 Kelvin to show you what happens. So, you see at higher temperature, again we start from the same number, only thing is that note down that the temperature is now 700 Kelvin. So, what we expect is that the energy difference will whatever energy difference was there, the effect of that will be reduced at that higher temperature, particle will start occupying, and yes, lo and behold, the number of particles at 3 different boxes are becoming equal now. So, it should not be exactly equal, should be little bit different. However, we expect them to have lesser difference compared to what we observe in 300 Kelvin. Now, stretch your imagination further and take it to a very, very low temperature. What do you expect? When you go to even lower temperature, the differences will keep on increasing, and now if you go on and go to almost like 0 Kelvin temperature, what you expect is that the difference will become infinite. So, e to the power minus 1 by 0, which means e to the power minus infinite, which means that other boxes should not have, and everything will collapse to one level, and that is what we known as the third law of thermodynamics, which says that the temperature at T equal to 0, the entropy value will go to 0, although we know that it is taken to be 0 for perfect crystalline systems, but statistical mechanics says that at a very low temperature it actually can collapse to one particular state. And we know for bosons, which for which all the several particles can occupy the same level, we have that Bose-Einstein condensation at a very, very low temperature.